plus the first times the derivative of the second. What's the derivative of r squared minus x squared? Negative 2x. Notice how Busis just glides over that r squared without even stressing about it at all, because it is a constant. Okay. Constantly stupid? Whoa. You should go hang out with Giles. You guys can just call every single thing stupid.
Stupid variable, this stupid chart.
Alright, so what do we have here? Now I will multiply things out. So this is r squared minus x squared minus 2x squared minus 2rx. Man, this was like really easy. It's way easier. Someone yesterday someone gave me a different suggestion and it was terrible and I didn't realize how terrible it was. This is just easy. Bam. That is my volume. Or that is my derivative. What do I do now? Probably like factor, right? You guys don't seem to be helping. Abandon the cause. So this is 3x squared plus 2rx minus r squared. Does that factor nicely? I feel like it must, right? 3x r and xr, please?
No.
Yes.
Yes.
Yes. Plus. Minus. Do you approve? Yeah, so what I get is that the derivative is negative pi over 3, 3x minus r, x plus r. So again, even though it doesn't make any sense for r to be negative, I will draw the entire number line because it's just easier to do it that way. So what is v prime? V prime has change of sign at negative r and r over 3. And because of the leading coefficient, it's like an upside down parabola, so it's like negative, positive, negative. Thus, where am I having a relative max? R over 3, yeah. So boom, max at x equals r over 3. Cool. So what I've just learned is that the best cone is the one in which this little bit is r over 3. And if that's r over 3, what's this? Well, I guess it's like root r squared minus r squared over 9. No, yeah. R squared over 9, which is the same thing as root 8r squared over 9. In other words, like 2 root 2 over 3 r squared. You guys see what I'm doing? I know I'm going really fast, but I feel like it's like okay. R. Yeah. Yes. So, the other thing I learned is that the radius of the cone is, the cone is biggest when its radius is 2 root 2 over 3 times as much as the radius of the sphere. Any cool? Alright, finally to finish it off, make sure the camera is in frame-ish. I will compute the volume of this cone. The volume of this cone is going to be, because I think they asked you to do that, 1/3 pi, well, it's just going to be r squared, so it's going to be, 2 root 2 over 3 r squared times the height, which is 4/3 r. So we get this giant mess, right? Pi over 3 times 8/9 r squared times 4/3 r. Final answer, 32 pi over 81 r cubed is the volume of this cone. Beautiful, beautiful number. All right. Gabriel, you're an expert on this now? Cool. Can I have this homework? Let's put it in a pile over there next to Rohan, and we got something to learn. Crap, 20 minutes not enough time. We'll just go fast. What? Sorry.
Video going on for Rohan. Video going on for Rohan.
That's what I'd be happy about. I forgot.
It's now our slaves.
The thing is, we both have spring break. Guess what the difference is?
We have to do the homework.
Yeah, we have to do the homework that you assigned us.
We have to study for APs.
You
One,
act
you
like,
have to
do
do
you
homework.
okay, can I pull up the definition of
Two.
break
And
for
the
you?
second difference is I get paid next week while you guys are just. Well, I'm doing
You don't get paid no matter what.
So, nice.
Yeah, but we get paid the same amount, so.
No, I don't get paid anything.
No, the same amount within the school and not.
Alright, good. Don't worry, you're all going to be making so much more money than me.
I'm gonna be like emailing you every day the definition of break, like not doing break.
All these, I'm going to San Francisco next week. Actually, Saturday. And I'm going to go visit all these alumni who are like 23 and they're working at Google. They're making like twice as much as I am. It's going to be really weird. They all came in here last week and were like, yeah, we work at Google. We had swordfish for lunch yesterday. I was like, what? Jerks. Like seriously, I don't think they were joking either. Alright, someone finish that board, 20 minutes left, we're gonna learn something, let's do it! Calvin, I want to talk about this thing called linear approximation. It's a little bit boring, so I'll spice it up with curves. What is a linear approximation? Alright, this is like kind of not a new thing. What a linear approximation is, what we're going to approximate a function using tangent lines. Alright, so I'll draw a nice function, maybe like so, and there is a particular place at which I am interested, and I'm going to draw the tangent line to the curve. And I'm going to make an observation that near this point A, this tangent line serves as a pretty decent approximation of the value of the function. In other words, if you were sick of using the real function and you wanted to just use the tangent line instead, you would be pretty close. Your y values would be pretty decent substitutes, as long as you don't go too far away from A, right? So if this is my function f, if I choose to anchor this tangent line at a particular point A, near A, the tangent line is like an approximation to the function. And lines are nice, and lines are not nice, and thus, sometimes I want to use lines. So what is the equation of this line? Emma.
F prime A.
Wait, can I get like the actual equation though? This is A comma f of A. The equation of this line would be?
Oh, y equals, y minus f of A equals f prime A x minus A.
Yeah, she's just giving me the generic equation of a line which goes to A comma f of A and has slope f prime of A, which is what the tangent line has. And now what I'm going to do, not for the first time, is think of this as a function. It's a function which takes some x and simply outputs f prime of A, x minus A, plus f of A. And this is known as the linearization of f at x equals A. This is the linearization of f at x equals A. Oh, by the way, I feel like our book is kind of crappy on this subject, so this lesson's going to be good, but our book's not good. So listen to me. All right. So, get it? Yeah, of course you do. What's not to get? Okay, problem. Find the linearization of f of x equals root x plus 3 at x equals 1. Go.
Yes.
All right.
Wait,
What's up?
no, you just.
To make a little picture of this, what does it look like? Root x plus 3 just moves this 3 to the left. It's going to be a little zoom zoom and a little zoom zoom. So it kind of looks like that. Yeah? Yeah. And if I draw the tangent line to this function at the point 1, that's like the point 1 comma 2, I guess, right? When I plug in 1, I get 2, yeah? So what is the derivative of this function? Well, I just have to do some math. This is all on camera, I hope. The derivative of this function is 1 over 2 root x plus 3. And so f prime of 1 is 1/4, yeah? Okay, so if this is 1/4, does it look like the slope of that red line is 1/4? Looks like it to me. So the linearization is just, it's going to be like, yeah, 1/4 x minus 1 plus 2. Is that what you guys got? Daniel, is that what you got? Yeah, can you erase the board also? Good. So, just this once, I will multiply it out because I just feel like it. So that's 1/4 x plus 7/4. Alright, so I am really happy with this. This is the linearization. Okay, again, this doesn't feel like anything new. The only new thing about this is, I guess I can use this now to approximate things. So for example, Matteo, suppose I'm interested in the square root of 3.98. And suppose I don't have a calculator. And suppose I do not know about this secret technique, which, I don't know, do any of you know how to find the square root by hand? There's an algorithm, it's on the internet, it's really hard and weird. Wallstein was really obsessed with it, he used to teach people. What? No, I want it to be hard. I want it to be 3.98. So suppose I was very, very interested in what the square root of 3.98 was. Well, it says me, please relate 3.98 to the current function at play.
It's 3 plus a little bit less than 1, which is relevant.
Yeah, specifically it is just actually just like f of 0.98, right? Yeah. Root 3.9 is just f of 0.98. So if I somehow, so it's like, man, damn, I wish I really knew what happens when I plug in 0.98 into this function. Well, I don't know, but I do know that the tangent line would serve as a very, very close approximation to 3.98, or to the square root of 2.98. And so what we're going to do is we're going to approximate 3.98. We're going to say that 3.98 is exactly equal to f of 0.98, which is approximately equal to, okay, of course it's equal, it's approximately equal to f1. I could just say 2 and just call it a day, but I want a little bit better than 2.
No.
Yeah, this is, the whole idea here is that this black curve is my function here, this red line is my linearization. And do you guys see how the linearization and the function agree like very, very closely? Near 1 at least, right? And this is pretty near 1. So just like Busa said, f of 0.98 is pretty damn close to L of 0.98. So compute L of 0.98.
L is exact like
What's up?
so like L is exactly
No, not really. Plug in, if you take 0.98 minus 1, what is that? Yeah, so this is going to be like 1/4 0.98 minus 1 plus 2. What's that? You guys see what I'm doing? It's like negative 0.02. So it's 1/4 times negative 0.02. Sorry, I'm going really fast. So are we okay with this ish? Y'all cool? So that's like negative a 50th, I guess, right? So it's 1/4 times negative 1/50th plus 2. Isn't 2.02 1/50th? Yeah. So that's like, what is that?
399 over 50.
Yeah. It's like 2 minus a 200th. 2 minus 1 over 200. Can I get that in decimal form? By being smart, not by using 99. Yeah, that's like a 200 is like half of 100, so it's like 0.005, right? Yeah, so this is going to be 1.995. Alright, so using basic arithmetic and just like my widths, I have approximated square root of 3.9 to be 1.995. Okay, now it's time for the big reveal. Stupid.
Whoa.
I know. We could just said 2 and called it a day.
Come on, man.
What a reveal.
Alright, so, if I happen to have a well, okay, I have a calculator, so, what is 3.98? Ooh.
I don't find that so wow.
You're not
I mean,
impressed?
like, because
You're not
we could have just said it was 2 a long time ago.
The other thing is, this is a lot closer to the real answer.
Alright, so this is extremely close. This is extremely close to the true answer. Why is it? I tried to impress you, but you guys are like. So you should be impressed. Why is it so close? It's so close because first of all, I picked a point which is really, really, really close to the place where I anchored my approximation. And second of all, I picked a function whose derivative is very, very small, so it's not escaping away from the function very quickly. Okay, but there it is. Okay, this is a little bit more than just a cheap trick to do things without calculators. It is in fact what we are really doing here is we are substituting for a line for a function. In other words, it's not just the case that I can use this to find individual points. What I can actually do is I can take this entire function, which is a line, and I can substitute this line in as a replacement for this annoying function. Anywhere where am I want to use it? What's up?
So this function, which is a line.
I can substitute in this linear function in place of my original f function. And this happens a lot like in physics. There are a lot of times when you do some physics and you find that the true description of what is going on is complicated and annoying and has lots of maybe like trig in it or terrible square roots, and you just like don't want all that to be there. And so what you do is you say, well, as long as I stay pretty close to this number, and I intend to, then this might as well be just like a line. And so if I'm only interested in things to be accurate up to a couple decimal places, then why don't I just use the linear approximation instead? Is this okay? All right. Good. All right. This is how I teach this subject. Your book teaches this very same subject in a completely different way with a totally different set of vocabulary. So please turn the camera over here. In the last 5 minutes of class, I'm going to reteach this entire topic, but in a different way. And the different way is introducing this thing called a differential. All right. So what are differentials? You'll find out in a second. The task initially is to do the exact same thing. I have some kind of function and I would like to approximate it. And so I pick a particular place at which I'm going to anchor my approximation at A. And this is A comma f of A. And in order to execute this approximation, I will use a tangent line. Whoa. Try that again. I'll use tangent line, and then can I get some red marker, please? And then what I'm going to do is I'm going to move over a little bit to a different point, and at that different point is where I intend to like actually do the approximation. So this is A plus delta x. All right, and the big idea here, so I'll just like write this down somewhere. Where? Okay, I guess I'll write it down right here. Here's like the big idea. The big idea is this process is useful when it is easy to compute. It is easy to compute f of a, and it is also easy to compute f prime of a. But it is difficult to compute f of x elsewhere. What's up?
When is this true, like in the real world when we have calculators?
Thank you.
Okay, so
I really appreciate that question.
Okay, so first of all, it's a theoretical understanding of how we, okay, so first of all, how do the, I mean, this is, there's a million answers I can have for this. This is more than just, well, like I said, I kind of gave you an answer already over there, right? I mean, the calculators have, you know, capacity for error, suppose you're doing billions of, I mean, there's actually a lot to say about this, but for starters, we'd like to know how the calculators even do this at all, right? And this is kind of what this is building towards. So that's one answer. This is building towards an understanding of how the calculators even do all these things. So that's important to know. All right, especially if you're an engineer or a computer programmer or something like that. I mean, definitely. So, I mean, we can play these all. When are we going to use these games forever? The answer is like never. So, all right.
Exactly, that's what I was saying.
But that's true for like 99.5% of everything you learn in every class all through your whole life. All right. So it's also true that most people you see on the streets you're never going to see again. So you might as well just walk around like punching people in the face. And taking them out.
Well, no, because then you might die.
Good. Back to the subject at hand. All right. So what is going on here? We are moving over by delta x, and the answer is that when I move over by delta x, that's my new favorite answer to when are we ever going to use it. Okay. And we're going to move up by delta y. But the big idea here is that it is difficult for me to compute values of this function exactly. And so delta y is the thing that I don't know, right? I don't know by how much this function changes when I move over a little bit. But what I can compute is how much y changes in the tangent line. And now I have this kind of triangle here. Well, this is, okay, so, and what is the slope of this blue line? Slope of the blue line is f prime of a, right? Slope of the blue line is f prime of a. All right, well, what we can do is I can write down what f prime of a is. What is f prime of a? Well, f prime of a is like dy dx, right? And I made a big deal out of convincing you once upon a time that this is a symbol which is not to be interpreted beyond like as it is, right? This is like a derivative. This is not a fraction. This is a derivative which is like a limit of a ratio. Now what I'm going to do is.
Good afternoon, Blazers. There is no high school intervention this afternoon.
I'm just going to treat these things as if they are fractions
this afternoon.
And I'm going to just multiply both sides by dx. And I get the dy is f prime of a dx. All right, you should be recoiling in horror from this like terrible blasphemy. I am suddenly like splitting up a limit as if it's like a thing, even though they're not things. These things are called differentials. And you can think of a differential as kind of like an infinitesimally small change in x and an infinitesimally small change in y. All right, well, if that's a differential, then this is like, this guy right here is dx. What's this? What's the height of that red thing? Yeah, that's dy. And so, what I'm sort of saying here is that the predicted change in y is the derivative times the predicted change in x. Okay, let's do a problem. The problem looks like this. Suppose I take a function, and all right, so what I want to do is I want to use differentials to estimate the cube root of 7.9. What is the cube root of 7.9 approximately? Well, can you think of what's a relevant function? The relevant function is f of x equals cube root of x. And where can I predict this function exactly? At 8, right? As Sandeep says, I know what f of 8 is. F of 8 is 2. And do I also know what the derivative of this function is?
1/3 x to the negative.
Yeah, 1 over 3 x to the 2/3. What is f prime of 8?
1 over 12.
1 over 12, thank you. Okay, and so the situation is, here's my, well, that's not the scale, this is all terrible. This is 8, and when I plug in 8 I get 2, so this is the point 82. And what I'm doing is I'm drawing the tangent line to this function, and this tangent line has slope 112. Follow? Okay, and what is then, what is the cube root of 7.9? What is it equal to approximately? Well, it is, here's the way you do this. I can finish just in 30 seconds. It is basically f of 8 plus the change in y. Okay? So it's the current value of the function at 8 plus the amounts by which the function changes. Yeah? Say yeah. Okay, and this is approximately equal to f of 8 plus the predicted change in y. Okay? Because this is what I can't do. Well, f of 8 is 2. What is the predicted change in y? Well, the predicted change in y is just the derivative at 8 times the change in x. And so we get 2 plus, what is the derivative at 8? 112. And by how much did I change from 8 to 7.9? Negative 1/10. And thus I get a really good approximation for cube root of 7.9 by starting with f of 8 and figuring out roughly by how much I change. And roughly by how much I change is the derivative plus how much x changed by. So what we get is like 2 minus 1 over 120. So whatever that turns out to be in decimal form, that's going to be a really good approximation of cube root of 7.9. Okay, good enough? All right. Lots of homework over break. Bye, internet.